Okay, so hello everybody. In this presentation, we will briefly describe two recent research works focused on the security of wireless communication protocols. These researches have been conducted in the LAAS-CNRS laboratory by TSF team, which is dedicated to safety and security. So my name is Romain. I'm a Ph.D. student, and my thesis is co-directed by LAAS-CNRS laboratory and Apsys Lab, which is a company specialized in computer security. My research thematic is mainly focused on IoT security, especially the wireless communication protocols widely used in IoT. I also would like to introduce my colleague Florent Galtier, which is another Ph.D. student working on wireless communication protocols. His research work is mainly focused on mobile networks security and especially 5G. Both of us are members of the TSF team, and our works are directed by Mohamed Kanish, Vincent Nicomet, and Guillaume Auriol. So this presentation will be split into four main parts. First, I will present the background and the research questions that have motivated the development of the two approaches presented here. Second, I will introduce one of our main contributions from an offensive perspective, named Mirage, which is an offensive framework targeting multiple wireless communication protocols, such as Bluetooth Low Energy, ZigBee, or N-Struct Burst. Third, Florent will describe our second contribution, which is a protocol agnostic and lightweight fingerprinting approach dedicated to the detection of IoT devices spoofing. And finally, he will conclude this presentation and talk about our future work. So, first of all, I would like to briefly describe the background of IoT and why we should care about the security of this kind of systems. Indeed, the IoT field has some characteristics that are problematic in terms of security. So, the first problem is that the technologies in use are heterogeneous in terms of software, hardware, and communication protocols. As a consequence, it's difficult to build a systemic approach in order to secure the systems. The second problem is linked to the rapid expansion of smart objects, leading to a competition between manufacturers to win new markets. Every vendor tries to release new objects or features as soon as possible, sometimes without adequate attention to security requirements. There is also a big problem with the lack of expertise and knowledge in security of these manufacturers. So it's mainly linked to the fact that lots of them are initially specialized in electronics and not in computer science. These systems are also generally tiny embedded systems with limited resources. So it may be sometimes difficult to integrate some complex security features such as cryptography. And last but not least, these systems are generally interconnected and have some characteristics, such as mobility, for example, that leads to complex and dynamical environments. So in this context, it may be really difficult to monitor and analyze this kind of environment. So in our opinion, multiple research questions are relevant in order to improve IoT security. The first question is how to detect and prevent intrusion attempts in this type of environment. So we are working on multiple approaches to detect and prevent attacks. However, building an intrusion detection system also implies to be able to evaluate its efficiency. So this question leads us to work on the generation of realistic attack scenarios and the simulation of an attacker's behavior. Last but not least, we need to be able to perform security audits in order to discover vulnerabilities, and ideally, these security audits must be reproducible and efficient. So the first part of this presentation will mainly be focused on the last two research questions that have motivated the development of Mirage, while the second part is linked to the first research question and explore a fingerprinting approach based on the analysis of physical characteristics of radio frequency signals. In the next slide, I will briefly describe the current situation in offensive security for IoT and why it's currently difficult to perform realistic attacks. So I mentioned previously the fact that multiple wireless communication protocols are currently used in IoT. Some of them are well known and are based on open standards, such as Bluetooth Low Energy or ZigBee, while others are proprietary and relies on security by obscurity, such as N+, for example, for sports devices. These protocols are heterogeneous and are rapidly evolving, complicating the development of generic tools and techniques dedicated to offensive security. The situation is similar considering the hardware components that can be used to perform attacks. As you can see on this picture, there are a lot of different tools that could be used in an offensive security perspective. There is two main types of hardware. Some of them are based on system on chips, and the others are based on software-defined radios. Generally, the hardware components based on system on chips are not initially designed to perform attacks, and it requires to write custom firmware or to use hacks and tricks to mitigate some hardware limitation. For example, one of the dongles in this picture, which is named Crazy Radio PA, has initially been designed in order to control an open source drone. However, it can be used to sniff and inject frames in a communication protocol named Shockburst, which is commonly used by wireless keyboards and mice, thanks to a custom firmware implementing an hack to add a promiscuous mode. The software-defined radios can also be used and are interesting because of their genericity. However, they are difficult to use and they may be too slow for some protocols based on channel hopping, such as Bluetooth Low Energy. All these hardware components also have heterogeneous features and APIs. Last but not least, the software tools dedicated to offensive security also present some serious limitations. They are increasing in number and variety, and most of them are mutually incompatible in terms of API, file formats, and hardware support. One of the biggest problems is linked to the use of high-level libraries, which are generally not adapted to the offensive security context. As an example, Galtier and Betelgeuse are two major tools in Bluetooth Low Energy security, allowing to perform man-in-the-middle attacks targeting BLE connections. They both use Noble and Blino, two Node.js libraries, allowing to simulate the slave and master role involved in a BLE communication. However, these libraries are not adapted to an offensive use and could not be used together on the same operating system. So it forces the developer of Betelgeuse to build a complex software architecture based on WebSockets to avoid this limitation. And the developer of Galtier has chosen to modify the source code of the libraries themselves, resulting in a forked version which is non-standard and difficult to maintain. So from our perspective, this situation is a break to the development of offensive tools. Indeed, it generates costly duplicate development and poorly written code. It forces security analysts to assimilate a lot of technical information, which are neither relevant nor reusable, as they are mainly linked to specific tools. And it also involves serious limitations on offensive scenarios automation. As a consequence, we need to rationalize the process of development of these tools and facilitate their use. So Mirage Framework has mainly been created to solve the previously mentioned limitations. As a consequence, it's based on 4 key principles which have guided its development. First of all, the framework tries to provide a unified API. So as a consequence, every tool provided by Mirage exposes a similar API, and the module development is standardized. Second, one of the main principles of Mirage is the modularity. So the attacks are split into reusable and modular components called modules. These modules can be combined together using a chaining operator which is similar to the Unix pipe, and it allows to build complex attack workflows. Their behavior can also be highly customized using a mechanism of bindings named scenarios. The third principle is the genericity. So the main idea is to allow to interact with different protocols and hardware components in a similar way. As a consequence, the framework introduces 2 abstract components named emitter and receiver, allowing to harmonize the use of different hardware components providing similar capabilities. The modules are also built according to their generic role, such as sniffing, simulating a role, or jamming. Last but not least, the framework allows low-level analysis of wireless protocols, The stacks are implemented at the lowest levels that can be accessed by software, allowing to avoid the limitation of high-level libraries. The communication with hardware components is also re-implemented from scratch, using standard dependencies to avoid the use of specific libraries. So, in the next slide, I would like to illustrate this principle by describing a specific use case of Mirage. So, I mentioned earlier that Mirage allows to combine multiple modules in order to build complex attack workflows. As an example, let's imagine you want to dump the firmware of a connected light bulb by extracting it during an over-the-air update process. So if you want to do that, you could use 5 Mirage modules chained together to clone the light bulb. So first, BLE-scan allows to sniff the advertisements. So the advertisements are messages transmitted by the light bulb in broadcast to indicate its presence. Then you can combine BLE Connect and BLE Discover to establish a connection with the light bulb to dump the application layers. So it allows us to get the internal state of the light bulb in order to simulate it later. Then you can use the collected information as input for BLE add and BLE slave, allowing to simulate a similar device. And BLE slave can be customized using bindings, so named scenario in Mirage, to mimic the over-the-air update process initiation. So here I have a video illustrating how to perform this attack. So here you can see the different modules that scan the advertisements, establish a connection with the light bulb, and dump the application layers of the light bulb. Then these information are used to simulate a fake light bulb. And as you can see, the mobile application has connected to the fake device and is initiating an over-the-air update process, allowing to get the firmware over the air. So at the end of the attack, we managed to get the firmware file. So here you can see the strings in the firmware. So currently, the following protocols are supported by Mirage: Bluetooth Low Energy, Zigbee, Wi-Fi, Instruct Burst, Mozart, and infrared. The framework has been used by ANSI during a research work on BLE presented at STIC last year and allowed to find dozens of vulnerabilities in commercial IoT products. The framework is still actively maintained and developed. So we have a lot of modules and libraries that are not released yet, with support for new devices, new protocol stacks, and offensive and monitoring modules. In the future, we would like to extend Mirage to automatize complex offensive scenarios, especially to evaluate our defensive approaches. And we also want to use it directly in a defensive approach to passively monitor the environment and detect wireless attacks. 2 papers describing this framework have been published, the first one at STIC and the second one at ESSRE.
Okay, so now I'll talk about a new monitoring approach we built against spoofing attacks in IoT. So what are spoofing attacks in IoT? There are attacks where an attacker will clone a given device and try to execute malicious activities instead in the network. The main problems, the main issues with those attacks in IoT are that they are easy to perform and hard to detect. Easy to perform because most of the time we have weak authentication schemes in IoT. They're often just checking the MAC address in transmitted frames in order to detect who is sending them data. And they're hard to detect, first because naive approaches like reception power-based detection are not that efficient, especially indoors, or if the attacker can modulate its emitting power. And second, because the link layer characteristics and upper layer characteristics are often easy to clone, as you saw in Romain's demonstration. So we need physical layer monitoring in order to detect those attacks. So in the state of the art, we have two main families of device identification schemes. They are first the transient-based identification schemes, which are based on what we call the transient period at the beginning of the transmission, which corresponds to the charging of the electronical components of the transmitter. So those approaches are quite efficient, but need high-end equipment in order to get enough data in such a short period of time. And then you have a second family of approaches, which are modulation-based, modulation dependent, which will take the signal coming from a device, compare it to an ideal modulated signal, and use the error between the two in order to identify the device. So the problem being that those approaches need to be redesigned for each new modulation introduced in the environment. So what we did is we tried to use the spectrum of a whole frame in order to fingerprint devices. What you can see here is the Ph.D, so power spectral density. So it's the spread of the power among the frequencies of the signal of 6 signals, 3 from one device and 3 from another device. So each device has its own color. And you can see that coming from a given device, the signals are quite similar, but between the devices, they're not. So the main pros of this approach are that it doesn't need high-end equipment because we can get enough data at lower sample rates because we take the whole frame. And it's protocol agnostic. We don't need the modulation scheme in order to identify devices. So we published a paper about this approach at PRDC 2020. Sorry. So how it works, we built a system based on that, working in 2 steps. The first one is registering the legitimate devices. So we will receive for each of our devices a set of a given number of frames. We will compute their PhDs and register them. Then we build a similarity metric in order to compare them and build a similarity matrix and run a community detection algorithm on this similarity matrix in order to put the different signals in communities depending on the device that emitted them. And we save this matrix and the communities in an additional database. Then we can pass to the second step, which is real-time intrusion detection. So we will listen to the medium. Each time we receive a frame, we compute its PSD and compare it with our similarity metric to the registered ones. Then we try to estimate in which community it will end. And if it's outside the known communities, it's considered a possible intruder, and an alert is raised to an administrator. So we tested this algorithm in Bluetooth Low Energy and ZigBee and got really promising results, even in the case where legitimate and illegitimate devices were from the same model and same manufacturer. Sorry. So to sum all of this up, we explored in our thesis multiple aspects of IoT security, both from an offensive and defensive perspective. And we are also actively studying low-level vulnerabilities on IoT wireless protocols, such as Wasabi, which we published at STIC, for example, which is an attack allowing to emit and receive ZigBee using a BLE chip, and Injectable, which, as the name implies, is based on a new way to inject inside the BLE communication, which is currently under review. So in the future, we would like to first work on using offensive strategies such as reactive jamming from a more defensive perspective. For example, using reactive jamming to prevent intrusions in IoT environments by jamming malicious packets. We would also like to combine the physical layer analysis I just talked about and the link layer analysis present in Mirage in order to create a kind of IoT SOC. And finally, adapt this approach of Ph.D.-based fingerprinting to 5G communications in order to detect, for example, spoofed base stations, or to assist authentication using physical layer characteristics. So thank you for your attention, and have you got any questions?